Albert Einstein concluded that nothing can travel faster than the speed of light in a vacuum. Frankly, he's right. The speed of light in a vacuum is the fastest speed the universe will allow. It's not just a suggestion, it's the law. Einstein also concluded that light can't travel faster or slower than light. The speed of light never changes, no matter what you do. Because the speed of light is not a variable, some crazy things happen when you change relative motion. Let's get into it. If I were to throw a baseball from the back of a moving van or a truck, the baseball would go a lot slower relative to the ground than to where I threw it from. In that case, our velocities add up. If I throw a baseball at 70 miles an hour from the back of the truck and we're moving at 35, the speeds will compile. And so the ball in relation to the ground will only be moving at 35 miles an hour. The same thing happens if I throw forward. The truck's going 35 miles an hour and I'm throwing 70, which means the speeds add up to 105. Light doesn't do that, though. It's quite crazy how light never changes speed. You could be, if you were moving in a space shuttle at half the speed of light and you shine the light forward, the light would still go the same speed. It would not go 1.5 times the speed of light. It would be going the speed of light, no matter where you are. It's all because the speed of light doesn't change, like, ever. Something has to compensate, though. Like, if I shine the light and I'm going forward, something has to change. And something does change. That something is time. If you're watching this channel, you may or may not have heard of time dilation. It basically is when you're moving fast, or even when you're moving slow, time shifts around you. And this is all because the speed of light has to stay the same. If we say I'm moving at half the speed of light through an empty part of space, and then there's someone moving at 0 speed relative to me, they shine a light. The speed of light, it has to stay the same. And so, like, for it to stay the same, something has to change. When I look out the window of my spacecraft and I see the light, if I were able to measure that light, it would go the speed of light. It would not go any slower or faster just because I'm moving fast. That's because when you move fast, the universe slows down around you. In order for the speed of light to stay the same, time has to be the variable. Distance is also a variable, but we'll get into that later. We'll take my flashlight here. I turn it on. Light traveling at the speed of light. You can't see it because there's no fog in the room, but you can see my hand is lit up, moving at the speed of light. But if I move the flashlight forward, the light is still traveling at the speed of light relative to me and relative to the flashlight. It's because the flashlight, when it's shining the light forward, and so to make that speed of light the proper speed of light, since it can't be anything else, it has to speed up. So, like astronauts that went to the moon, because they were moving so fast, they aged a few seconds less than everybody here on Earth did. Astronauts on the ISS will age a few milliseconds less than the rest of us here on Earth will. The difference is negligible, but it's there. There's another thing that has to change, and that's distance. Okay, back to the spaceship. The spaceship's traveling at half the speed of light, and then someone else shines a light in the direction of travel, let's say. So something has to change. We've already got time, but since, like, speed is measured, velocity is measured in units per unit of time. So people run in meters per second usually, but some things are traveling miles a second or miles an hour. And so when we do this with light has to stay the same speed. So to stay the same speed, we can't just change the hour or make the hour shorter. We have to make both miles and hours shorter. If you were able to measure the speed of light with a meter stick, basically what would happen is your meter stick would shrink. Since it shrunk in the direction of travel, that makes the meter less. And since time is going faster outside your vessel than it is inside, then it makes it so that the speed of light is the same no matter where you are. I'm going to quick pause myself here in the middle. This is kind of a breaking point. So if this doesn't make any sense to you and I didn't explain it well enough, let me know in the comments. Also, if you want another video where I explain it better, maybe, if this wasn't adequate, let me know. Anyway, back to what I was saying. So these are all Einstein's theories of relativity. The light travels always at the same speed. There are a bunch of other aspects. I'm going to get into a few of them here. Don't worry, we'll get into E equals mc squared. Not right now. Okay, number one, gravity does not travel instantaneously. So the sun, it's exerting gravity on the Earth, and the Earth is exerting gravity on us and the moon. If the sun were to disappear, we would not, the light would disappear maybe 8 minutes from now. But nothing can travel faster than the speed of light. So the gravity has to travel at the speed of light or slower. And it turns out it's been tested that there are gravity waves. If we imagine it like a trampoline, and you have a bowling ball and then you have another bowling ball, they're going to exert gravity on each other. When you take one away, the other bowling ball shifts, but not instantaneously. It's the same with the fabric of space-time. When you take something away, it doesn't just disappear. It doesn't change all at once. It travels in waves. There are actually people that built a gravity wave detector, and what do you know? They detected a gravity wave. Number two is that light is also affected by gravity. Light can get sucked into a black hole. Also, light will bend around something with high enough gravity. There's an instance of this where we can see the same supernova 4 times, all because the light was bent around another star. But the speed of light has to stay the same. And when you're under gravity, if you're accelerating, so if my right fist is a black hole and my left, like my fingers, they're light, they get close, they get sucked in, but it's not just going to travel at the speed of light. It needs to travel faster, but it can't because it's the speed of light. So what happens is when the light comes in, the light doesn't go any faster, but the time slows down. And so if you were here in the event horizon and you just stayed there by some miracle of magic, you would see the rest of the universe age a lot faster because the speed of light has to stay the same, but time warps around it. So under stronger gravity, your watch will tick slower than someone's under less gravity. All right, the moment you've all been waiting for. E equals mc squared. That is kind of a thing that people say to make them smart. Like my brother, he once said, just to make himself sound smart, he was like, y equals mx plus p equals mc squared. I was like, you don't know what that means, but I'm about to teach you exactly what E equals mc squared means. So let's break it down like we did in algebra. So like with y equals mx plus b, each variable is a value. So y would be the y value, but in this case, it's E equals mc squared. The squared is fairly simple. We can get that out of the way right now. E, energy. M, matter. C is the speed of light. I don't know why it's C, but it is. So let's take C out of the equation and just replace with the words a very large number, because that's basically all the speed of light is. It's just a very large number. Now you take mc squared and you get E. If you rearrange the equation, you can get the square root of energy over the speed of light equals matter. So basically, if you take a lot of energy, then you square root it, then you divide it by the speed of light, then you get an amount of matter. And that amount of matter is a very small amount of matter compared to the amount of energy. Basically, all this equation is saying is if you get a lot of energy, you can make a little bit of matter, or you can take a little bit of matter and make a lot of energy. There are 2 examples that I have to share with you. I can't do any hands-on experiments with them because I don't have a particle accelerator, but let's do the first one. So if you have an antiproton and a proton, they're attracted to each other. They'll come together. The antiproton, let's just give it an abstract value. So -1. It is -1 and the proton is 1. They come together, they annihilate, like we add them together and they make 0, but they produce a lot of energy. You can also do this in reverse with quarks. Quarks are bound together And so when you pull them apart, they want to spring back. It's like a spring. And so if we pull them apart, once we put enough energy into them, we stop there. Once we put enough energy, that's a lot of energy. And so it's enough energy to make 2 new quarks. And so you have 2 quark pairs. You just made a little bit of matter with a lot of energy. All right, that's it for this video. I hope you enjoyed it. It does not take a lot of energy, does not take enough energy to make any matter to click the like and subscribe buttons. But anyway, thanks for watching.